Hello, everyone. This is Veysel, Head of Data Science at Johnson Controls, leading the healthcare NLP team at Johnson Controls for the last 5 years. So, welcome to NLP Summit, first of all. So, I'm going to cover the measuring the benefits of healthcare-specific large language models today. And then we are going to see some metrics and then how we evaluated our recent LLMs and then how it should be done and what we have observed while doing this evaluation. Okay. So, as you know, Johnson Labs offer healthcare NLP and medical LLMs. Like so far, the healthcare NLPs are flagship product by Johnson Labs, which is developed by our team, globally distributed around the world, by the way. So we are a fully remote company. And then healthcare NLP is the library that hosts more than 2,000 pre-trained models and pipelines that can extract everything that you see on the right side of my screen. So it basically extracts entities, finding the relationships, and then maps these terminologies, map these entities to certain terminologies like ICD-10, SONOMED, etc. As well as it can do many other classification or segmentation kind of tasks. So, but on the left-hand side, we also have medical LLMs. Even before the ChatGPT era, we have been working on the LLMs, but people do like encoder-based, transformer-based models, like word-based models we have been using, and then we have been integrating these transformer-based solutions into our workflows and to help our customers as well. Then, for the last 2 years, we have been developing and some, as well as fine-tuning some medical large language models, and then we put them under 5 different categories like MED-S, MED-M. All these suffixes represent the size of the model. So if it is MED-S, it is less than 3 billion. If it is MED-M, it is less than 10 billion. By the way, anything that comes less than 10 billion size of LLMs are already included in the healthcare NLP library. So you can use with your license by using the same notebooks that we share in our workshop report. Then we have MED-L, like greater than 40 billion. So we have 50 billion size, 70 billion size, etc. These are all medically fine-tuned on a data set that we created internally, as well as some research data set that people are already using, like researchers are already using in the other papers. But we fine-tuned on an internal in-house annotated data set most of the time. So we have MedRag, which MedRag is like a retrieval method generation based 3 billion size medical LLM models, which means that you can handle LLM component of a RAG with less than 3 billion size of model. And we have MedNav to extract name identities from a medical context by using 3 billion size of model. We also have medical chatbot and generative AI lab. So on the left-hand side, you see LLMs, and the right-hand side, you see the classical healthcare NLP model that we have been shipping for the last 5 years. So these LLMs comes in various sizes, as I explained. So and each one of them is designed to be used for certain purposes. For example, MED-S can be used for summarization and question answering, while MED-M can also be used both summarization and question, but also closed book questions. For example, open-ended closed book questions that you don't provide any context. You just ask like how to treat asthma kind of questions. And then MED-S NAR can be used for name identity recognition because it's only fine-tuned on that purpose, so it doesn't do any other task. So that's why you need, and right now the library comes more than 20 different models from these dimensions, because each one has different versions for different tasks as well as different quantization levels. So fine-tuning LLMs, is it worth it or not, right? So recently in April, there's a paper called LoRaland, because we have been fine-tuning LLMs with the help of LoRa framework, as you know, which makes it very easy to fine-tune with your own data and then change its behavior, the model's behavior, as well as move the parametric knowledge of the model into your own space. Right. So in this paper, researchers claims that LoRa fine-tuning significantly enhances the LLM performance, even surpassing non-fine-tuned based LLMs as well as GPT-4. So as you see in this chart, all these different LLMs are compared to their base model when you fine-tune, right? So like the red indicates the delta between fine-tuned versus base model, and as you see, almost all of them gains too much value when you fine tune this. Of course, generalized model has their own benefit, because if you don't have a specific task in your mind, you may not hit the same target with the specific fine-tuned LLMs. But if you have a specific task, let's say you are only filling out some forms based on a speech-to-text transcription, or you are only doing some summarization or some Q&A based on a context, you don't need a generalized model, right? So you can have some small model, which will be more feasible to deploy on your local, as well as you can scale further and cheap, etc. But if you need a generalized general test like a chatbot assistant, you can do many other things under the sun. Of course, you may need a larger models, right? So, but this paper evaluates the like non-medical, like evaluates the LLMs over a non-medical benchmarks, including mainly all the other data sets out there, benchmark data sets. And then, as you see, before fine-tuning versus after fine-tuning, we see that fine-tuned models surpass GPT-4 by an average of 10 points across various tasks. But these are all public benchmarks, so there is no clinical context. Even if there are some tests like chemical and disease recognition, these are only just like a minority of these tests that you see on the left-hand side. So that's why we wanted to think about how to do this in a medical context. Luckily, there's a recent paper which just came out like a month ago, which is called MEDIC, to evaluate clinical grade evaluation of large language models. Before even this paper, we have been setting up some experiments and then measuring. We have our own benchmarks and then own dimensions. Just like you see the evaluation dimensions here, we have our own dimensions, which looks very similar to this one, but luckily this paper already underscores the ideas that we have been discussing internally at the company. So MEDIC offers 5 dimensions to evaluate any LLMs in a medical context. It's like medical reasoning, ethical bias, data understanding, in-context learning, and clinical safety and risk. These are all the important dimensions and criteria that if you really want to evaluate any LLMs in a medical context fairly. Similar to this one, as I said, we develop our own dimensions, evaluation criteria. So we pick MED-M and MED-L, like less than 10 billion size and greater than 40 billion size, 2 different LLMs that we fine-tuned internally, and we evaluated this against GPT-4o. And then we use 3 dimensions over there, by the way, like we pick factuality, clinical relevance, and conciseness. If you have seen my previous talks in the other summits or other venues, we have been evaluating our medical chatbot. The other models we have been comparing our different classic healthcare NLP model versus GPT-4, and then we had used similar metrics over there as well. So this is not something new for us. We basically, in the factuality, we try to assess whether the answers contain verifiable and truthful data based on the medical knowledge and existing sources, as Rater uses his own knowledge over there, by the way. And clinical relevance, so relevance and applicability of the information to clinical practice. Conciseness is like a brevity and clarity of the answer. As you know, some LLMs likes to talk a lot, so there is some verbosity over there. So conciseness is very important over there as well. So we generated 400 questions, 400 plus actually, more than 450 questions from scratch. We have our own physician annotators. They are human medical doctors. With the expertise and experience that you see on the slides. For example, one of them is a professor in a pathophysiology, another one is a hematologist, another one is neurologist, and all of them have at least 2 to 3 years of experience in AI and NLP solutions. So they are not just we just didn't pick them from nowhere. So they have been working on these kind of solutions and evaluations and labeling tests for the last 2 to 3 years. And then we evaluated these questions over 4 different tasks: medical summarization, medical question answering, biomedical research, and open-ended QA in clinical notes. So to evaluate this, we set up a randomized blind evaluation. So randomized blind evaluation means that at each row, as you see, we gave them an Excel sheet on the on the slide. You see like a snapshot from my Excel sheet. So basically, they don't know which model belongs to which model alias. We call it model 1, model 2, and model 3. So they don't know which model corresponds to which actual model. So sometimes model 1 is MedM, sometimes model 2 is MedM, depending on the row. And sometimes model 3 is just GPT-4. So they don't know. They only see the question, prompt, they only see the prompt, category, the context text, and then the answers from each model across different dimensions: factuality, clinical relevancy, and conciseness. So we evaluated pairwise comparison. Why? Because it's easy to evaluate pairwise rather than asking which one do you pick or rate your answer. Rate the answer from LLM. We just ask them, okay, which one do you prefer? Model 1 versus model 2, model 1 versus model 3, etc. And then they can pick 4 options or 5 options. They can say model 1, like a model on the left hand side, model on the right hand side. They can say neutral, which means that both equally correct, and they can say none. And then they do this for each pair combinations. And then we also assign 3 physicians out of 4. We assign 3 physicians to same set of seed data set, 400, 100 question each, to measure some inter-annotator agreement. But in our evaluation, they annotated, like each one is annotated 100 question out of 400 question, like 1 to 100 is a rated 1, like the second 100 is rated 2, etc. But for inter-annotator agreement, we assigned them 100 questions again out of another data set, and then we try to measure the agreement level. We also did washout period analysis, but I'm not going to explain this in this slides. We basically wanted to see how often they change their mind. So it was really hard to evaluate this. Why? Because especially when I tried to analyze the results, I had to keep track of which line model 1 correspond to which LLM, etc., and then try to make sure that I have a fair evaluation, and then I don't just mess up just by writing the wrong code. So that's why we have validated our results again and again, and this is the first result that we see. It's amazing to see that just 8 billion size of model, medical fine-tuned model on a summarization test, by the way, is doing better than GPT-4 on 100 question for summarization. By the way, out of 400, 100 summarization, 100 Q&A, 100 and 100 from each task in short. So that's why we wanted to have a same split for each task. And then as you see, factuality, when it comes to factuality, 8 billion size of model is preferred for 7% of the time compared to 25% of the time for GPT-4o. And then 22% of the time, they were both equal. So, and then relevancy is also 48 to 25, and then conciseness is 42, because this is not surprising for us for conciseness actually, but for the others, we of course we are glad to see these results, but we wanted to evaluate why this happens, and then the other papers and research also already validates this observation. Then there are some sample questions that you see on your screen. So we basically didn't just summarize this. We asked summarize patient's medical history, summarize the backgrounds, summarize the discharge information, etc. This kind of granular level of summarization task that you might see in a real-world setup. Then this is question answering in clinical notes, the second category, second task. So you see some sample question over there as well. So it's basically given a clinical note as some question, like what is the prescription, what is the medication prescribed to patient, what are the procedures ordered for this patient, etc. Or some biomedical research papers, and then as some question to the context. So over there again, factuality, there's a 10% gap between our model versus GPT-4o. So this is 8B versus GPT-4o. I just wanted to highlight again. And then most of the time they are equally preferred. So if you distribute the neutral on both sides, the delta will still be same. So it's basically like around probably like 50% to like 50% to 40%. You will see these numbers, right? Including excluding the nuns, right? 50% GSL, MedM is preferred, 40% of the time GPT-4o preferred, and then 10% of the time it is done. And relevancy 12% delta, and conciseness again 12% delta. So it's again 8 billion model beats GPT-4o over there. Biomedical research, that is the in biomedical research the delta is much bigger, because we fine-tuned our models on clinical context, biomedical context, some Q&A, some summarization tests that we might see in a real world setup, right? And you see some sample question. Biomedical research is basically you provide some article or some PubMed paper, and then you ask some question to that paper to abstract, or you just ask some biomedical questions directly given a short paragraph. Okay, and most of the time when it comes to clinical relevancy, it is important to see that neutral is preferred most of the time, which means that models are usually perform same, but when you distribute, you will see the same delta again. So the 8 billion size of models still again beats GPT-4o in a biomedical research. So open-ended Q&A, this is the only place that we couldn't beat in clinical relevancy. Why? Because in clinical relevancy, because this is open-ended QA, you don't provide any context. The questions are just closed book questions, like how to treat asthma, what biopsy techniques to confirm malign bone tumors, etc. These kind of questions that you can just Google or ask, or try to find an answer from the official resources or clinical practice guidelines, right? So over there, since LLM itself, GPT-4o itself is a more generalist model. It is probably beating 8 billion model, even if we fine-tune, because there's no way we can generate a data set to cover all the medical knowledge in the world, right? So that's why it's understandable, but conciseness again, it's head-to-head 2% worse than GPT-4o, but factuality, we are 5% better than GPT-4o itself. So overall metrics. So if we just average all of them, this is the chart that we see. So 8 billion model is 5% better than GPT-4o when it comes to evaluating these 4 tasks, right? So clinical relevancy is again head-to-head. So we are 1% worse than GPT-4o, but conciseness is more than 10% better than GPT-4o itself. So the factuality is one of the most important dimension over there, and then it's great to see that we are doing 5% better than ChatGPT just by fine-tuning 8B model. And then if we distribute the neutral, because neutral means that they both preferred at the same time, right? Like they both correct. If we distribute evenly on both sides, factuality is 46 to 41, which means that for 6% of the time, 8 billion size of model is preferred for factuality against GPT-4o. And then relevancy, it is again head-to-head, and then conciseness, of course, 8B is much better. Why? Because conciseness, because we can control the conciseness while fine-tuning the model, because it's depending on the data set that you use to fine-tune. So overall, 8 billion model does better than GPT-4o on a certain test that we pick over 3 different dimensions that we pick to evaluate our models. Then we did another interesting experiment. What if we use GPT-4o itself as a judge? So we asked the same question to GPT-4o. It's like our 5th rater. So we already had 4 rater, right? So we asked GPT-4o itself to do this comparison, to do this evaluation. And it's clear that GPT-4o favors its own responses over other models' responses. As you see, the red ones are GPT-4o preference. So it is doing 50% better than our MedM model. But this is quite interesting observation, because GPT-4o strongly disagrees with human medical doctors that we use on 2 dimensions. Factuality and clinical relevancy, it just favors its own responses. Conciseness, it says, okay, GSL model is better. Of course, we don't give any clue over there as well, but given its writing style, etc., probably it can recognize. And recent research also says that you see at the bottom of the page, LLM, recent research already illustrate that LLMs have a non-trivial accuracy at distinguishing themselves from other LLMs. So it already understands and then can recognize LLM its own input, its own output, sorry. and then it's that would be the reason probably. So this is not just our observation, it's already observed by other researchers as well and then published as a research. Then we calculated the intra-class correlation coefficient. So intra-class correlation means that assessing the reliability and agreement among writers. And when we do this evaluation for all the dimensions, for factuality, for example, we see that we see negative agreement, which means that raters that there is a poor agreement when it comes to factuality across different readers. But when it comes to consistency and clinical relevancy, they started to become more agree each other. So basically, raters are consistent in their assessment, but do not agree each other most of the time. So that is what this table tries to say, by the way. So they are consistent with their own assessment, but when it comes to compare rater 1 to rater 2, they don't agree each other most of the time. So this shows the subjective nature of LLM evaluation. And then if you compare the dimensions against each other, raters are less consistent and in agreement in factuality than they are in clinical relevance and conciseness. So this is also something that we already has seen in the charts. But factuality says that they are in factuality, when it comes to factuality criteria, they are mostly inconsistent. But they show some consistency across other dimensions. So key takeaways. If I summarize everything that I tried to explain here, in short, Johnson Labs healthcare-specific LLMs beat GPT-4 by around 10% on the tasks we measured after fine-tuning on domain-specific data set. This observation is already verified by other researchers and other papers. We basically try to do the same, but we use our own data set and annotation and optimization technique, and then we are happy to see that we have test-specific LLM that we can use, and we have been already using in production to solve certain problems without using any cloud-based large LLMs. And this is achieved by 8 billion size of model, which can be deployed on premise, running privately and efficiently without any internet connection. And this is a randomized blind evaluation done by medical doctors. So even if they don't agree strongly each other, they were consistent in their observation, which is a big plus. But evaluation needs to be done across multiple dimensions. That's how we set this up. And subjective nature of LLM evaluation highlights the importance of developing proper metrics, question, and evaluation strategies that we have been trying to explain in this presentation. And evaluation requires medical expertise. As you see, we have 4 physicians, and then they all come from different backgrounds, but they even make some mistakes, and which requires nuanced clinical knowledge to uncover for us to understand the underlying reasons. And evaluation hard. Evaluation is really hard, even for the other simple machine learning model. This is not black and white, as you see. So that's why we wanted to measure inter-entity agreement. We wanted to fit the specific task, and some we wanted to fit to the certain data distribution rather than a generalized model. And then things may go wrong while doing this. If we wouldn't be careful while doing this calculation, because it's a complex analysis, if not paying attention, we may end up with a different picture. So that's why we want to make sure that our numbers check in. And then we are happy to see that we are at least 5 to 10% better than GPT-4o on certain NLP tasks with just 8 billion size of model. Thank you for listening to me. I hope you enjoy the rest of the summit. You can contact us in different channels. Have a great day ahead.